We're in chemistry, chapter 16, and we're going halfway through, and we got to the oxidation numbers, which takes a little thought and putting a number to oxidation. This is the way that scientists classify. So we had these rules that I went over already, but I'll review them a little bit. So rule number 1 is the oxidation of a number of element in its uncombined state is simply 0. So if we have anything like chloride, diatomic molecule of chlorine, or hydrogen or nitrogen or oxygen, these are all going to be 0. Or S8, these are polyatomic, and which are many put together of sulfur or phosphate. Again, this number is going to be 0. That's the first rule. Second rule is that the oxidation number of a monoatomic, there's only one atom ion and equal to the other. So we have one ion here, like sodium is an ion, chlorine is an ion. When they divide out, and these charge would be whatever charge they are in their form that they're binding. So you have sodium is going to be +1, chlorine negative, calcium is going to be +2, oxygen is going to be -2, and these will be, we'll figure these out, so we can figure out their numbers as either +1 or -2 by just their valence numbers there. So, and on to rule number 3, hydrogen always is going to be +1, unless it's in at the end like lithium hydrogen here, but otherwise it's going to be +1. Oxygen is always going to be -2, so unless it's a peroxide, and because the peroxides combine a little bit different. And then rule 5, halogens, which halogens are in the periodic table in 17, column 17, and the halogens are like fluorine, chlorine, bromine, iodine. Those are common halogens, and they are going to be a -1 unless they're bonded in a whole bunch of in a bigger molecule. So, and then rule 6, alkali metals, which are group 1, 2, on to 13, those are their combinations. They just have the positive oxidation valence charge that they would normally have. So potassium would always be a +1, and calcium would always be a +2. But that's when they're alone. So the problem is now most of these atoms don't occur alone. They turn into molecules and bond together. And so rule 7 is how we bind them together and how we count them. So we have to take the algebraic sum of the oxidation numbers of all the atoms in the molecule, and they must be equal to the charge on that molecule, okay? And that's what we were doing, taking the algebraic sum of all of them, and it has to be equal to whatever charge. If the charge is 0, they have to be equal to 0. If the sum is -2, it has to be -2. And so that's what we were doing in these problems here. And we did these problems, basically taking the algebraic sum, and to find the sum, sometimes you have to find, okay, we don't know what chlorine is, but we knew oxygen. So basically we knew the oxygen was going to be, has 7, and it's going to be a -2, so that'd be -14. And then chromium has 2, so 2x plus -14 equals what? -2 charge. So you add them together, and you'll have to get a -2. So x equals, if you figure this out, to figure out what that chromium x is going to have to equal, there's two chromiums, so you have to divide 12 divided by 6. So see how I did that? So they're not that hard. So now we're going to go to the oxidation numbers in redox reactions here. And basically, so when an atom loses an electron, it's oxidized. When the charge of the atom becomes more positive, therefore oxidation is a process in which the oxidation number increases. So now we're going to look to see, does this number that we're giving it, does the number increase or does it decrease? So if it increases, it's going to be the oxidation process in which it is oxidized. Similarly, if the reduction, the gain of electrons, is a process in which the oxidation number decreases. So as the oxidation decreases, I just think decreases, reduction, then we know that it's being reduced, or whatever is a process in which the oxidation number decreases. So we need to find, does this number increase or decrease? So that's kind of important. We need to know that. And so here's an example of it here. And so we have 2 sodiums and chlorides equal sodium salt right here, right? So this is a pretty easy one. So of course that's going to be 0, you know, because we know that basically in its state here there's not going to be a charge on it yet, and there's not a charge on the chlorine because it's coming in 2. Remember, it says if you take these alone, they're going to be 0. And so that, but then we're going to, as we have combined them, you know, we had +1 and -1, which equals 0 too. But so we have to make sure that you sign these numbers. This is a very easy one, but you're going to find a lot more complicated than that. So the oxidation number of sodium is increased from 0 to, see this one, 0 to +1. And this one is changing from 0 to -1. So it's reducing. See how this is getting less and this is getting more, but they're staying equal in the combination. So the oxidation number of chlorine decreased from 0 to -1 and therefore underwent reduction. So this one's sodium is getting larger, so it's oxidizing. And then chlorine is getting smaller, so it's reducing or under reduction. So just to know, we can look at this in any equation now. So it's a handy way. So here we're going to determine the oxidation numbers. This is kind of important because they actually, you'll see as they described it, they skip the stage that's over here and just, you know, okay, do this stage first, thinking we already did it. So, and that's made it a little bit more complicated. But here we're going to determine the oxidation numbers for each of atom in these reactions. We're going to take zinc here, zinc and onto silver nitrate, and we're going to see how they react. And we have to put oxidation numbers with each one. Zinc, silver, nitrogen, oxygen, all have to have numbers. And so that's the part, figuring out those numbers. So first of all, what do we know here in this one? First of all, we know we're going to take, if we take, let me see how I did this so I can show you to find the numbers. The oxidation number of zinc has increased. You can see oxidation number of zinc has increased over here to 2, so it's going under oxidation. You can see as for zinc has been oxidized and is the reducing agent. And you'll see the oxidation number of silver here being +1, it has decreased from +1 to silver over here being 0, and so that has been reduced. So the substance containing the element silver nitrate is the oxidation agent, because it's, as you can see, the oxidation agent is from what? Going from 1, let's follow that green, to 0, +1 to 0. So the oxidation number of zinc has increased from 0 to +2. So zinc has been oxidized and is the reducing agent. So 0 to +2 is oxidized, and it's the reducing agent, just the opposite. The oxidation number of silver has decreasing right here from +1 to 0, so the silver has been reduced. It got less, right? The substance containing the element AgNO3 right here, this substance here, is the oxidation element as it's oxidizing. So you got it? It's not too hard. But if we had to figure this out, we'd figure this out over here, which, you know, I did pretty easily. In fact, here's how I did it. So you can see, you'll see there, you see the +1. How I did that basically is, you know, x equals whatever. So I ended up finding out +1 equals -1 in that situation. But you don't have to do that right now. So we're going to go on to this one here and find out which is the reducing agent, and which is the reducing agent and the oxidizing agent in the midst of this combination. So let's go look and see how they put that. The oxidation number of sulfur has decreased from 7 to 6. So sulfur has been reduced. The substance containing the sulfur atom is the oxidation agent. The oxidation number of iodine has increased from -1 to 0. So let's look back and see that on the problem. Okay, you see right here, we have the sulfur. Here is +7, and you can figure this sulfur out to get this 7. You have to get this 7 by doing this method over here, but which I did, but I don't think we need to do right now, but basically going through here. But it was 7, and this is, of course, oxygen is a -2, and then 7, we look at the sulfur over here, it's going from 7 to 6. It's reducing. So as it's reducing here, you see as it's reducing, it's going to become the oxidizing agent as it's reducing. But here we have iodine's going from -1 to 0, so it's increasing. So it's actually oxidizing because it's increasing. So as it's increasing, it's oxidizing. This one is decreasing, so it's reducing. But the oxidation agent is going to be the one that's reducing, which is going to be S2803. So if they ask you that question, it's going to be the one that's reducing. Okay, now they're going to do, this is quite a deal. I went through this whole thing in my notes, which you have to do to really figure it out. It's not as complex as it looks. Let's just say that. So let's we're gonna go over the steps of balancing this balancing the equation and the summary of rules. But here we go. It says, up to this point, we have balanced equations by inspection, following a few simple guidelines. Unfortunately, many redox equations are difficult to balance by inspection because of the number of terms involved. However, oxidation numbers provide a different and less complicated method for balancing redox equations. Remember how hard sometimes it's to balance. The method we follow here is based upon the fact that in a balanced redox equation, the total decreased in oxidation number must equal the total increased in oxidation. They have to be equalized out. The steps for balancing redox equation by the oxidation number method are given. So how they're going to balance, they're going to say, okay, now we can balance by this oxidation number, balance both sides, and we can figure out where to put our coefficients and what we need to do to balance our equations. So these are our rules here. So again, the steps. Rules, or I shouldn't say they should be steps. Here's the steps. First, we're going to write the unbalanced net ionic equation. Just write it down. And then by inspection, or actually before inspection, we're going to assign oxidation numbers. Each one of them have to have oxidation numbers. See all these oxidation numbers, +1, +3. They're all going to have to have numbers. And we already went over how to do those numbers. So that takes a step right there to do those numbers. And then we have to determine which one are undergoing oxidation. So basically what we just, are they getting smaller, or are they getting bigger? So which ones are assigned these numbers are undergoing oxidation. So that's number 2. There's actually kind of two things. You're assigning the numbers, and then you're figuring which ones are going under oxidation, which we just talked about. Then in number 3, by just looking at it, inspection, we're going to individually balance each atom to make sure they're balanced, that are undergoing a change in oxidation number. So we're going to look at the ones that have the change in oxidation number, those ones, and we're going to balance those ones that we see that are going under oxidation, not the other ones. And number 4, we're going to determine the total increase and decrease in this oxidation number for each type of atom, so we know what's increasing and what is decreasing. So same as we're kind of doing up here, finding out which one's increasing and which one's decreasing. And then we're going to determine the factors necessary to equalize an increase and decrease in oxidation numbers. So we're going to put coefficients to make them equal. and coefficients are basically in front of each one to make these, to balance these oxidation numbers. So, which so far it's been pretty easy. And then we're going to balance, we're going to go, and now we have to look and balance the remaining atoms. So we did these are the oxidation numbers that we, atoms that we did first. And now we're going to do the ones that are just, the spectators or the ones that are there. They need to be balanced too. So we're going to balance the remaining atoms, but not the hydrogen and oxygen until the end. So we're going to start balancing the other remaining atoms. If there's any other remaining atoms, sometimes there's not. And then we're going to go and start balancing the hydrogen. So we're going to deal with hydrogen. When we deal with hydrogen, we're going to basically deal with it, whether it's acidic, an acid, remember, hydrogen ions make it acid, or OH, hydroxide ions, make it basic. So we are going to take either of those, but now whether it's in an acidic solution or not, or a basic solution, we have to have those solutions to add them to. So water may be added to achieve the balance for the oxygen atoms, so we can. But do not confuse the charges with the oxidation numbers. Just kind of stay with those oxidation numbers. Otherwise you'll get mixed up, and you'll see how to do this. So anyway, you're going to add hydrogen, and then right at the end, you're going to balance the oxygen out and make sure the balance, everything is balanced. Every single molecule is balanced in it. So this is what they did here. So let's go back and see how they did. So first, they assigned these numbers. So here's our equation. And they assigned, basically assigning these numbers. And I knew how to assign these numbers. So I kind of, this stage, if you look here, you can see how basically assigning these numbers. So we have the chromium 2 and oxygen. Chromium and oxygen, so to figure out this number is 6, we don't know that 6. We don't know what this number is. So we end up saying, we know that oxygen is going to be negative 2, and we have 7 of them right there. So we say 2x, we know there's 2 chromiums, 2x plus 14 equal a negative 2. And so we end up 2x adding the 14 on both sides here, and you get 12, dividing, and you get 6. But we already did this in another problem. So here we know that the chromium is 6. The same way with the carbon and oxygen here. Oxygen has negative 2 charge, and so we don't know what the carbon is. So with a negative 2 charge, we basically said, okay, this is you're going to have to add these two together, and they have to get this last charge, negative 2. So we have, we put x as carbon, so there's 2 carbons, so 2x plus a negative 8, because negative 2 times 4 equals a negative 8, equal negative 2. Subtract, or basically add 8 to the negative 2, and you're going to get 6. So 2 divided by 6 is 3. So you now know the carbon number is going to be a 3. Over here we know chromium is 3 plus, so in the midst of chromium being 3 plus, that's the valence charge it normally is. And then the carbon dioxide, we know the same way. Carbon dioxide has to equal, so carbon, we don't know what carbon is, but we know that oxygen here will be negative 2, and you have 2, those will be negative 4, and so now you have x equal 4, because they have to equal 0, which is no charge there, so carbon would be 4. So just to know how I got those numbers, that's what we did before. So here we have the numbers, 6, negative 2, 3, 2, 3, plus 4, negative 2. We already figured these out. Chromium and carbon are undergoing oxidation. Let's look. Which ones are getting bigger and which ones are getting smaller? Chromium is a plus 6 and it's getting smaller. So it's going to plus 3. So it's getting smaller. Carbon is 3 here, but it's 4 over here, so it's getting bigger. So they're both getting going through oxidation. So So there are 2 chromium on the left, but only 1 on the right. And so we give the chromium 3 a coefficient of 2 to equal the numbers. So what we want to do is equal those numbers out. So how do they do this? Basically, they put a coefficient here of 2 in front of the chromium because they need 6, right? We have 6 here. We're trying to balance these numbers out. So we have 6 here. We only have 3 here. So we're going to put 2 so we can make this 6 and this 6. So these two will be equal. The same thing with the carbon over here. So we have the carbons 2. This is a little bit more complex, but how we're doing this. But basically, this will have to be equal to 6 and in the midst. So this one's a little bit harder. So here we already did this. So this one we're going to balance out by putting a 2 in front of this one. So, okay, let's see. Here we go. This one is reducing. So see here, 2 times -3 equal -6. But anyway, here's reducing. Let me show you this. It's better that I show you on my notes because I kind of went through this. So this here is reducing. We figured that out. Number 2, the oxidation is happening here. And so we have the change here going on, change in one and the change in the other. So as you see, I guess you can look on here about the same. So anyway, 2 minus 3 equals 6, and 2 times plus 1 equal 2 here. Since both chromium and oxygen and chromium contain 2 atoms of the element undergoing an oxidation number change, we must multiply the change per atom. So it's going to be -3 for chromium and +1 for carbon, and you have to multiply these by 2. See, that's what they did up here. Since you have the changes being 6 going to 3 is a negative, 6 going down to 3 is a -3, so we have to take -3 times 2. So, and then on to the same one, you have one change going down, or going up, I'm sorry, +3 to +4, and then you're going to multiply that by 2 to get the total charge of each atom. So now this has to be the total charge. So now to equalize the oxidation number, we must multiply the coefficients by a factor of 3. So this is 2 times -3 is going to be -6, and then we have here 3 times 2 is going to be +6, so they're equal. So what we're going to have to do is, this is 2, we're going to have to multiply this by 3. So this is going to be 3, and then this is going to be 3. See how we added those so that these two would be equal. Since there are no atoms left to balance other than oxygen and hydrogen, we can proceed to step 7. So now we have to, in step 7, what's step 7? We're going to be dealing with either hydrogen or hydroxide. So there's a total change of 8 negative on the left and a total change of 6 positive on the right. Okay, since the reaction is an acidic solution, we add hydrogen to balance it. So see how they add hydrogen, because here we have basically 6 and 8. What's the difference between 6 and a -8? Okay, if you put them together, you're going to get a -14, or a +14, I should say, because 14 times 1 equals, so anyway, we're going to get 14. If you add 14 hydrogen, so we added 14 hydrogen here to balance the hydrogen out. To balance the oxygen out, we're going to add water. So we look at the oxygen then. It says to balance the oxygen atom, we need to add water to the right side of the equation, since there are 7 plus 3 times 4 equal 19 oxygen atoms on the left and only 12 oxygen atoms. So you're going to add the oxygens on this side and you're going to get 19. Oxygen on this side, you're going to get 12. So now what is, you look at 12 and 19, if you subtract them, you're going to get 7. So you're going to put 7 H2O. So see how they added the water to balance the oxygen. They added the hydrogen to balance the hydrogen. And so now we find that each side has 14 hydrogen, 2 chromium, and 19. Look on each one of these, and all of the ones on this side, each one should equal the ones on the other side. See, it gets kind of complex, but not really if you just take them in steps, which I did. And you have to do it yourself to really figure it out, because when you just look on here, you think, what are they talking about? So, but when you're doing it and balancing out, it goes easier. So let's go on to the next. Okay. Strengths of oxidizing and reducing agents. So let's talk about the strengths. Okay. You can see in oxidation that there are some agents that are commonly used more than others, like zinc. Zinc is a good one to use as a reducing agent. And also the halogen chloride is a good used in oxidation too. And on to similar MnO4 is permanganate right here. They use that a lot because that's a very good oxidation agent. Just some work better. Zinc has a large tendency to give up electrons, and so it becomes oxidized very easily. So it's a good reducing agent. And then of course the permanganate right here, MnO4, is also +7 in the oxidation set, so it has a large tendency to become reduced. And it's a strong oxidation agent. There's others as chromium, dichromate, and sulfuric acid, nitrate acid. All of these are very strong agents to use if you want to do an experiment with them, that's for sure. So a strong oxidating agent readily acquires electrons in a redox reaction to be changed into a form that is a weak reducing agent. So similarly, strong reducing agents such as alkali metals or zinc readily lose electrons to be changed into a form that is a weak oxidation agent. This is reasonable since a substance with a large attraction for electrons, a strong oxidating agent, will not readily give them up, a characteristic of a strong reducing agent. So these are lists here. This list here is very important. The list here says the relative strengths of some common oxidating agents and reducing agents are in here. And you can see the relationship. Any reducing agent on the right column must be oxidized by the oxidation agents below it in the table. So, for example, let's look in this table. So we have the strongest reducing agents and we have the strongest oxidating agents are opposite from each other. So if we take the metal Ag, which is silver. So let's look down here and look where silver is. Silver is down here. Let's move it up. So here's silver. So silver, it will oxidize, right? Silver, for example, silver can be oxidized to the ion of silver by any oxidating agents that are below it, not above it. So that means it can be oxidized. All of these agents down here below it, always has to be below it. They can be oxidating agents to make silver into that ion, to oxidate silver. Okay, so as for the opposite, they took a metal oxide by oxidizing agent below it. They took iron. So let's take iron. So we have iron. So iron can be oxidized by any of those that are below it 2. So will be displaced by, so any of these come in this side, all of these that are below it can be oxidized. So we have anything, just remember that ferrous, which would be iron, Fe is iron, will be oxidized from iron to copper, will be reduced to copper when a strip of iron is placed in a solution. So if you take a strip of iron and you place it in a copper solution, will it be reduced or not? Let's look and see. So here is iron. Let's look where copper is. Copper is below it. So yes, it's going to reduce. They're going to have a reaction because copper is below it. So also, you take a strip of copper and will it be displaced by silver. So let's take copper. Here's copper. Where's silver? Below it. So yes, it's going to be able to, since silver is below here, it's going to be able to be reduced. A strip of copper will displace silver because it's below it. Just see if it's above and below it. So here's a picture of iron reducing the copper here in the midst. You can see what's happening here. And here's a picture of the copper reducing the silver. But all it is looking on this chart, which is pretty easily. You look on the chart and see where they are, and if they're below it, and now if they were above it, they wouldn't work. It always have to be below because the strongest one would have to come to reduce the weaker ones, I should say. So anyway, whew. Okay, that's it.